Now in this lecture we will try to understand more about wave formation in closed string. So I need you to pay close attention in this topic because the rest of the chapter is very much dependent on the concepts that I will be pitching in this lecture. Okay, so try to grasp all the knowledge that I'll try to give in this lecture with an open mind. Okay, and if you feel any problem, then feel free to ask me. Okay, so there is a closed string which is clamped between two rigid ends. So what will be the first vibration or the first wave which this string can provide? So this is the string, okay, initially at this. So what you will do is pluck from its between and like this, and then you will leave. So you can see it will vibrate like this, it will keep on vibrating like this. Okay, so what happens is that when you are plucking from the midpoint of it and you are leaving, so this becomes your incident wave, which goes which strikes here, gets reflected, and then here again it gets reflected. So this wave again, this, so this takes place consecutive in successive time intervals. Okay, now we know that at x equal to 0 there is a node, at x equal to L there is again a node, and in this point there will be an antinode. Okay, so in this diagram try to identify how many number of waves is in this disturbance. Okay, so you need to figure that out. Now suppose this part of the wave, is nothing but the positive displacement of a wave. Okay, and this part of a wave is the negative displacement of that wave. Okay, so this is equal to wavelength of this wave. You can see this is positive half and this is negative half, so positive half and negative half. So one complete wave is there in this situation. Okay, so in this case you can write number of waves, which was n, was equal to 1. Okay, now you have to relate this lambda with the actual length of this string, which is L. Now you can see that you are going from this to this, or this length is equal to L. Okay, this length is equal to L from here to here, L, and then you are again coming back, which is your this negative half of wave. So this is again L, so this is also is equal to L. Okay, so you can write that lambda is actually equal to 2L. Okay, now frequency mu1 can be written as V upon lambda. Okay, and we know that lambda is equal to 2L, so V upon 2L. V will actually be is equal to under root T upon mu, where T is tension in string and mu is mass per unit length. Okay, so you can write this as mu1 is equal to V upon 2L. Okay, this is also called as fundamental frequency. Okay, fundamental frequency because this represents the first wave which is formed in this closed string scenario. So this is also called fundamental frequency and first harmonic. Okay, now let's see another case. Okay, so in this case this string was plucked once. Okay, now in the following case there is this same string stretched between two rigid ends, and the length of string is also L in this case also. Okay, but we will plug this string in 2 points. In this case we plugged it in 1 point. Now we will be plugging it in 2 points. So the possible points of plugging will be this point and this point. So if we plug it here, it will be somewhat like this. So the graph is not exactly up to scale, but you get the idea. So if we'll plug like this, okay, we'll plug like this, and in this point we will plug like this and then leave. Okay, like this we will stretch and then we will leave. So what we will, if this is your wave, so this becomes your reflected wave. Okay, in this case you need to identify how many number of waves are there in this string or in this medium. So you can see that clearly actually, and this length is L. Okay, now you can see that if, see, this is one wave, you can see that clearly. So this is your one wave, and this you can see it is second wave. So this is your second wave. So we can see that there are two number of waves. So you can write that number of waves n is equal to 2. Okay, now you have to relate its wavelength with L. Okay, now you know that this is equal to lambda and this is also equal to lambda. Okay, now while going through this first wave from this point to this point, traveling a distance of lambda, that is also equal to L. So from this to this distance, this is also equal to L, and from here to here it is also equal to L. Okay, so you can write overall that 2 lambda is equal to 2L. See, lambda plus lambda is equal to L plus L. So you can write that lambda is equal to L in this case. So frequency, the respective frequency for this case will be equal to mu2 will be equal to V upon lambda. Again, lambda is equal to L, so that is equal to V upon L. Again, V will be equal to under root T upon mu. T depends whatever the tension is in this string, and mu mass per unit. So since it is the same string and same string, this is same string, in first case we plugged it once, in second case we are plugging it twice, so tension and mu remains the same, so the velocity doesn't change. Okay, so comparing, let this be equation 1. Okay, so mu2, compare this equation, okay, with this equation, you can see this will be equal to 2 mu1. Okay, so this is also called as second harmonic, or it is also called first overtone. Okay, now let's discuss one more another case in which, in this case we plug this we plug this medium or string once. In this case we plug this string twice. Now we will be plugging this string thrice. Okay, so let this be your string which is clamped at rigid ends, and now we will be plugging this string thrice. So the diagram is not actually perfect, so you can see that we have plugged it over here, we have plugged it over here, and we have also plugged it over here. So if this is your incident wave, then there will also be a reflected wave which will look somewhat like this. Okay, so in this case, okay, I forgot to mention these are antinodes and these are your nodes. Okay, there are 2 antinodes and 3 nodes. Again, in this case there are 3 antinodes and node, node, node and node, 4 nodes. Okay, now in this case again you first need to count the number of waves which is present in this condition. Okay, so draw a diagram. See, count the waves. This is your first wave and this is your 1.5 wave. See, from here 1 and this is your 0.5. So 1.5. Again this wave returns, so this completes a wave 2. Up till here it's 2 number of waves. See, 1.5 and again 0.5, so 2 number of waves, and from this point to this you can see there is 1 wave from this point to this. So overall there is 1, 2 and 3 number of waves. So this overall length can be written as equal to 3 lambda. Okay, now for this case you can see that we traveled a distance in, this is your length of stress string. Okay, so from here to here you moved a distance of L. So from this point to this point, okay, it's from 1.5. so 1.5, this length is equal to L. Okay, and again this length is also equal to L. So we can write that 3 lambda is equal to 2L. Okay, so from this we can write lambda is equal to 2L by 3. Now let's write the equation for frequency. That can be written as mu is equal to V by lambda. Okay, which will be mu3 is equal to V by lambda will be equal to 2L by 3, where V is equal to under root T by mu. Since the string is same, so tension and mu remains the same, so velocity is also same, which was here, here and here. Velocity does not change. Okay, so we can write mu3 is overall equal to 3V by 2L. Again, if we compare this with equation 1, okay, so mu3 can be seen is equal to 3 mu1. This is again called third harmonic or second overtone. Okay, so in this case you have to see that this was for n equals 1, this is for n equals 2, and in this case there were 3 number of waves, so here the number of waves n was equal to 3. Okay, so for each case now count the number of nodes and count the number of antinodes. Okay, so in this case number of waves is number of waves n is equal to 1 and number of nodes and number of antinodes. Again in this case number of waves n was equal to 2, so again number of nodes and number of antinodes. You need to count that and write as I go forward in this lecture. Number of waves n is equal to 3 in this case, number of nodes and number of antinodes. You can see that number of nodes is how much? 2 in this case, and here number of antinodes is 1 in this case. Here number of waves was 2, and you can see number of nodes is 3, and number of antinodes are how much? 2. Again number of nodes is number of waves is 3, number of nodes 1 2 3 4, number of nodes 4, and this is 3. So you can write an empirical relationship by the following observation, that for wave formation in closed string. Okay, first of all, point 1, number of waves is equal to n, so the number of antinodes will be n, and number of nodes will be n plus 1. Okay, for 1 you can see here is 2, n plus 1, and this is n itself. For every case you can see that. Now frequency in each case you can see is an integral multiple of the first frequency or fundamental frequency. Frequency in every case of n, which case? Number of waves. Okay, number of waves. So frequency in every case is integral multiple of fundamental frequency. Okay, always remember these 2 points. Okay, this is very important, and the concepts that I have discussed in this lecture will again be used in closed and open organ pipes. The idea remains the same, and the application I have taught in this lecture. Okay, so if you have any problem in understanding, feel free to ask, and in next lecture I'll be discussing more on the location of the nodes and antinodes. Okay, so see you in next lecture.